What if I told you that the key to understanding complex scientific concepts is hiding right inside the fantastical world of Pokémon? I'm Kyuka Wobodo, but in this scientific safari zone, you can call me Professor Baobab. Welcome to episode 11 of Poke A Mon. Which Pokemon will enter Hooper's portal into the scientific dimension this week? Quick disclaimer, this podcast is not affiliated with the Pokemon Company, Game Freak, or Nintendo. I'm here to use the storytelling power of Pokemon to unlock the marvelous mysteries of science. Dive into Frontiers of Pokemon Research, a free ebook that reimagines your favorite Pokemon as subjects of scientific discovery. Is Pikachu's 10 million volt Thunderbolt deadly? Why is Eevee's DNA unstable? How come Mega Charizard X is blue? It's all here! Sign up for my weekly newsletter and I'll send you this exclusive journal to spark your imagination and ignite your curiosity. Don't miss your passport to a world where science and fiction collide. What's up, Science Squad? Professor Baobab here. And if you've ever wondered why things always fall down, why the Earth and the other planets and stars are the same round shape, and why it is so easy to defeat gravity, make sure you don't fall asleep. I will begin with a summary of what gravity is. First, gravity is a force according to Newton's law of universal gravitation. Next, gravity is not a force, according to Einstein's theory of general relativity. I'll clarify this apparent contradiction, and I will also mention gravitational waves and the theories associated to explain the quantum nature of gravity. This introduction to gravity will help us unpack the Pokédex entries of Palkia, the spatial Pokemon, and a member of the Pokemon of Myth, or the Creation Trio. Gravity is the invisible force that governs the universe. It causes objects with mass to exert a pulling force on one another. It's what keeps our feet planted on the ground, the moon orbiting Earth, and the planets spinning around the sun. At its core, gravity is the mutual attraction between two masses. Likewise, it is a fundamental force of nature that operates on all scales, from the smallest particles to the vast structures of galaxies. Gravity is the architect of cosmic order, as it directly shapes the motion of celestial bodies and dictates the very fabric of our existence in the universe. This fabric is called space-time, a four-dimensional continuum that combines the three dimensions of space with the dimension of time. I talked a bit about space-time in my episode called Black Holes with Gardevoir. Our understanding of gravity has evolved over the millennia. Sometime around 350 BC, Greek philosophers like Aristotle proposed that objects fall because they seek their natural place. However, it wasn't until the late 17th century, 2,000 years later, that gravity received its first mathematical treatment. You know his hero story well. In 1666, a young Isaac Newton was sitting under an apple tree when a falling apple inspired his thoughts about gravity. While this tale might be oversimplified, Newton's resulting work was revolutionary. In 1687, Newton published his Principia Mathematica, which introduced the law of universal gravitation. He proposed that every particle in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This elegant mathematical description explained everything from falling apples to planetary orbits and its unified terrestrial and celestial mechanics for the first time in history. However, Newton's theory had limitations. It couldn't explain Mercury's orbital eccentricities, how much the orbit deviated from being perfectly circular. Perhaps most strikingly, it implied that gravitational effects propagate instantaneously across space, which violated the preconceived idea that nothing can travel faster than light. Enter Albert Einstein. In 1915, he published his theory of general relativity, fundamentally reimagining gravity not as a force, but as a consequence of space-time curvature. According to Einstein, massive objects warp the fabric of space-time, and what we perceive as gravitational attraction is actually objects following the natural paths, known as geodesics, through this curved space-time. Einstein's theory made several bold predictions. It suggested that light would bend around massive objects, subsequently confirmed during a solar eclipse in 1919, that time would pass more slowly in stronger gravitational fields, now routinely accounted for in GPS satellites, and that accelerating massive objects would create ripples in space-time called gravitational waves, finally detected by LIGO in 2015. Since that first detection in 2015, our understanding of gravitational waves has expanded dramatically. The LIGO-Virgo collaboration has observed dozens of gravitational wave events, mostly from binary black hole mergers, but also including several binary neutron star collisions. The 2017 detection of GW170817, which is simply the way astronomers refer to gravitational wave signals, GW stands for gravitational wave, and 170817 is the date the wave was detected. The 17th of August 2017. The detection of GW170817 produced by merging neutron stars was particularly significant as it was the first gravitational wave event also observed through electromagnetic radiation, what scientists call multi-messenger astronomy. The Kagra detector in Japan joined the global network in 2020, improving our ability to pinpoint where gravitational waves originate. This growing network of detectors has revealed fascinating phenomena. For instance, we've observed black holes that theoretically shouldn't exist in what's called the upper mass gap, challenging our understanding of stellar evolution. We've also detected binary systems with surprisingly misaligned spins, suggesting complex formation histories. Of course, when I say we, I don't include myself, but the team of scientists that worked on this project. Recent upgrades to the detectors have increased their sensitivity, allowing us to detect more distant and weaker signals. The future Einstein telescope and Cosmic Explorer promise even greater sensitivity, potentially allowing us to observe gravitational waves from the early universe itself. Speaking of Einstein, special relativity fundamentally changed our understanding of space and time. Rather than being separate and absolute, Einstein showed that space and time are intimately connected in a four-dimensional structure we call space-time. The theory rests on two primary postulates. The laws of physics are the same for all observers in uniform motion relative to one another, and the speed of light in vacuo, or in a vacuum, is constant for all observers. Special relativity is essential because it reveals that gravity isn't just a force, it's related to the very structure of space-time. Here's the crux. Gravity is a force if you look at it through the lens of Newton, but it is not a force when you look at it from the perspective of Einstein, which paints a more accurate picture of the so-called fundamental force we know and love. Nevertheless, special relativity only deals with inertial or non-accelerating reference frames. The limitations of special relativity in describing accelerated motion and gravity led Einstein to develop general relativity, where gravity emerges from the curvature of space-time itself. According to special relativity, as an object's velocity approaches the speed of light, time dilates or slows down, and lengths contract in the direction of motion. This is given by the Lorentz factor, which I will only mention in passing for the sake of brevity, but it single-handedly explains why massive objects can never reach light speed. The Lorentz factor is central to understanding how space and time behave at relativistic speeds, i.e. close to the speed of light, but it operates within the framework of classical physics, the domain of Einstein's theory of special relativity. However, when we examine the universe at the smallest scales, where quantum mechanics reigns supreme, new challenges arise. Reconciling the smooth fabric of space-time described by relativity with the probabilistic, discrete nature of quantum mechanics is one of the greatest unresolved questions in physics. This brings us to one of the most perplexing challenges in modern physics, quantum gravity. Einstein's theory beautifully describes gravity at large scales, and quantum mechanics excellently explains the behavior of matter at tiny scales. But these two fundamental theories are incompatible. At extremely small distances, the Planck length, about 10 to the power of minus 35 meters, or incredibly high energies, we need a quantum theory of gravity to merge these two frameworks. Perhaps it would come as no surprise that developing one has proven extraordinarily difficult. The leading approaches to quantum gravity include string theory and loop quantum gravity. String theory suggests that all particles and forces, including gravity, arise from the vibrations of tiny one-dimensional strings in multiple dimensions, as opposed to the point particles described in the standard model, a topic I go into more detail in particle physics with Eternatus. Loop quantum gravity, on the other hand, proposes that space itself is quantized into discrete units at the Planck scale, much like how matter comes in discrete atoms. According to this theory, the fabric of space-time is envisioned as a quantum network, where each node represents a fundamental unit of space. Both theories face significant challenges. String theory requires extra spatial dimensions that we haven't observed, while loop quantum gravity struggles to recover our familiar smooth space-time at larger scales. Neither theory has produced experimentally testable predictions that would distinguish it from its rival. Some physicists are exploring alternative approaches such as causal dynamical triangulations or asymptotic safety. The quantum nature of gravity might seem far removed from everyday experience, but it becomes crucial when we consider extreme scenarios like the interior of black holes or the first moments of the Big Bang. In these situations, both quantum effects and gravity are strong, and our current theories break down completely. In seeking to unify the principles of relativity and quantum mechanics, quantum gravity not only deepens our understanding of the universe, but also challenges our very notions of space and time. It suggests that the fabric of reality may be far stranger and more complex than the smooth space-time we experience on human scales. This blending of physics with its interplay between geometry and probability mirrors the kind of abilities that science fiction often attributes to cosmic entities, such as bending space-time, transcending dimensions, or even altering causality itself. And that brings us to Palkia, the Pokémon said to govern space. Could it be that Palkia's domain taps into the very concepts we've been exploring? By wielding power over space, it might reflect the strange and beautiful ideas from the mathematics behind Einstein's theory of special relativity, quantum gravity, and the dynamic nature of space-time. Let's take a closer look at how these scientific principles might manifest through Palkia's godly abilities. I'm going to state the Pokédex entry and which game or games it belongs to. I will then analyze it. Finally, I will render my verdict, deciding whether or not the entry is logical or scientific. The Pokédex entries from Pokémon Pearl, X, Omega Ruby, and Shining Pearl state, it is said to live in a gap in the spatial dimension parallel to ours. It appears in mythology. A gap in the spatial dimension evokes ideas central to advanced theories of physics, particularly string theory and its extensions, which suggests that additional spatial dimensions might exist beyond the familiar three-dimensional space we experience. String theory posits that the universe contains up to 10 or 11 dimensions, depending on the version of the theory. These extra dimensions are hypothesized to be compactified, meaning they are curled up at incredibly small scales, making them imperceptible to us. If Palkia lives in a gap in the spatial dimension parallel to ours, this could imply it inhabits one of these higher dimensions, unbound by the limitations of the four-dimensional space-time we perceive. In string theory, the interaction of strings within these hidden dimensions gives rise to the particles and forces observed in our universe. Palkia's presence in a parallel spatial dimension could suggest that it exists in a domain where these strings vibrate differently, granting it unique properties, such as the ability to manipulate space. It may also mean that Palkia spontaneously generates the fundamental forces that we experience. Additionally, string theory introduces the idea of brains, short for membranes, which are multidimensional objects. Our universe could exist on a three-dimensional brain within a higher dimensional bulk space. Parallel brains could represent entirely separate universes or realities existing within the same higher dimensional framework, but disconnected from our direct perception. Palkia's gap might correspond to a region within the bulk, a space between brains where different spatial dimensions interact. Such a gap could serve as a liminal zone where the usual rules of space-time do not apply, enabling Palkia to influence space across multiple dimensions. Living in a gap between spatial dimensions could also explain Palkia's ability to distort space. In theoretical physics, transitions between dimensions or branes might involve phenomena like wormholes or quantum tunneling, which allow particles or entities to move between otherwise inaccessible regions. If Palkia has mastery over these mechanisms, it could appear to transcend ordinary space and exert influence over it, bending or twisting it from its interdimensional vantage point. Verdict: string theory is still in its infancy, and we have yet to discover a unified theory of everything. Still, the idea of a parallel universe and pocket dimensions have been hypothesized in different contexts, and the scientific plausibility thereof cannot be overlooked. The Pokédex entries from Pokémon Heart Gold and Soul Silver state its total control over the boundaries of space enable it to transport itself to faraway places or even other dimensions. According to Einstein's theory of general relativity, space-time is not a static framework, but a dynamic, flexible fabric that can be curved or warped by the presence of mass or energy. For example, massive objects like stars or black holes bend space-time, which we perceive as gravity. Additionally, phenomena such as gravitational waves, ripples in space-time caused by the acceleration of massive objects such as black holes and neutron stars, demonstrate how space can be distorted dynamically. If Palkia can distort space as described, it would obviously imply the ability to manipulate space-time at will, either by generating gravitational fields of extraordinary magnitude or through some other mechanism outside our current understanding. This ability could manifest in several scientifically intriguing ways. Palkia could potentially compress and stretch space locally, akin to the theoretical Alcubierre warp drive, which proposes faster than light travel by contracting space-time in front of a spacecraft and expanding it behind. Such manipulation could allow instantaneous travel or even the creation of shortcuts like wormholes. Alternatively, distorting space might involve introducing discontinuities or anomalies, effectively creating bubbles or regions where space behaves differently. This could explain how Palkia is able to teleport without the need for a wormhole. However, achieving such feats would require an immense amount of energy. In physics, the energy needed to significantly distort space-time is proportional to the mass or energy presence. For instance, even a small black hole requires the mass of several stars to generate its intense curvature of space-time. For Palkia to manipulate space freely, it would either need to possess a source of infinite or near infinite energy or operate through mechanisms beyond our current models, such as tapping into the quantum structure of space-time itself. All in a day's work for the firstborn child of Arceus. Another speculative avenue is that Palkia might utilize exotic matter, a hypothetical substance with negative energy density that appears in some theories of quantum gravity and advanced physics. Exotic matter is a key component in theoretical constructs like stable wormholes and warp drives, which rely on negative energy to sustain spatial distortions. Verdict: there is nothing God's Son cannot do. However, it is also potentially scientifically plausible. We just haven't developed the instruments to measure stuff like exotic matter yet. The Pokédex entry from Pokémon Legend Arceus states, "This Pokémon is feared as a deity in Hisuian legend. The birth of Palkia was what caused the walls of our world to disappear, creating a sky that spans for infinity." The walls of our world disappeared can be interpreted metaphorically or as a literal description of a profound spatial transformation. If we take it metaphorically, it might signify a shift in perception or understanding of space itself, much like how real-world scientific revolutions, such as going from Copernicus's heliocentric model to Einstein's relativity, expanded our conception of the cosmos. The disappearance of walls could symbolize breaking free from a limited, bounded view of the universe. If taken literally, the walls could represent physical boundaries such as a closed or finite space-time geometry. In cosmology, certain models describe a finite but unbounded universe, like the surface of a sphere, where space loops back on itself. Palkia's birth might then be imagined as an event that removed these boundaries, transforming the universe into an open, infinite structure. Meanwhile, the idea of an infinite sky introduces several layers of interpretation, both scientific and philosophical. In reality, the sky we observe, the observable universe, emphasis on the word observable, i.e. what we can perceive, is vast but finite. Its size is limited by the speed of light and the age of the universe. We can only see as far as light has had time to travel since the Big Bang, making the sky approximately 93 billion light years in diameter. Beyond this horizon, the universe may continue indefinitely, but we cannot observe it. If Palkia's birth caused the sky to span for infinity, it suggests an alteration that eliminates observational limits, perhaps by transcending the speed of light constraint or creating a new space-time topology. Space could either be flat and extend forever or loop back on itself like a gigantic sphere. Philosophically, a sky spanning for infinity might reflect an existential idea. The boundlessness of possibility, freedom, or divine power. The Hisuian mythology framing Palkia as a deity aligns with this interpretation, portraying it as a cosmic being capable of altering reality itself to create infinite potential. Verdict: Palkia might have inherited omnipotence from Arceus, but this is also scientifically plausible, especially since we don't understand the sheer magnitude of infinity and have no way, currently, to observe beyond it. I hope you understand the gravity of understanding gravity. Gravity isn't a force in the most rigorous sense, but it is fine to still talk about it as a force. There are a lot of strange implications regarding gravity not being a force. I talked about this in my video episode on my channel, Magnets Aren't Scary at All, linked in the show notes. Anyway, I'm sure you now have a deeper appreciation and fascination for Palkia. Let me know if you want me to cover another legendary Pokemon in the comments. Science Challenge! Before our next episode, I want you to do something crazy. Think of any legendary Pokemon and try to explain its defining ability using science. Let me know which Pokemon you chose and I might call out your name in the next episode. My email address is chuka1000@hotmail.co.uk. It's also in the show notes. What did you think? Isn't the power of science simply amazing?